Now we are in the realm of analysis. The word divisor will be mentioned, but not so much. So what I tried to describe last time, at the end of last hour, was that if you have a trisecant of the Kuma variety of a Jacobian of a curve, then by degenerating you get an equation k of q, which du k of q, which du squared plus dv k of q is 0, and then by expanding in Taylor series get a hierarchy of differential equations. A hierarchy is just a nice way for us. I won't describe what a hierarchy really means, and I won't explain at this point what an integrable system means. So it means it's completely integral. It has all the integrals you would like to have, but let's not worry about. So an infinite sequence of PDEs. Okay, and the theorem of Shota is the first PDE is enough to characterize Jacobians and then the theorem is that just this being true for some q is enough to characterize Jacobians, essentially, but I'll say this more precisely later. Of course, this is a very ad hoc method. I just wrote down the trisecant, I degenerated it somewhat, and I got a sequence of equations, and I somehow told you that this is called a KP hierarchy. And you might wonder why people would study such a strange thing as KP hierarchy if they didn't know about the trisecant. And this was in fact the way it happened. So what I want to do now is I want to take a huge step sideways, and I'm going to discuss a completely different subject. So this is a subject about PDEs, essentially, or about ordinary differential equations, depending on which guys you cast it. So this is a question about commuting differential operators. Okay. So suppose we have a differential operator L1. So this is going to be the following differential operator. It's going to be a sum of ui of x, or I goes from 0 to say n, of d dx to the I. Right? So this, I just wrote down a general differential operator in one variable. Right? I'll be sloppy here as to whether x lies on R or x lies on C. Historically, what happened, people started differential operators with real, in the real domain, and then it turned out that under the assumptions we're going to make in a second, they all extend to the complex in a nice way, so it doesn't matter. But I'll skip over this. So consider such a differential operator. So if you see such a differential operator and you would like to know something about its eigenvalues or eigenfunctions or something like that, you can try to simplify it. So, you know, if you try to solve a cubic equation, you can try to solve a general cubic equation. But then, of course, you can set the highest coefficient to be equal to 1. The same you can do here. So we are going to assume that un of x is a constant. That maybe I'll denote C if the need to denote it something arises. Okay. Moreover, if you're trying to solve, you know, a cubic equation, if you ever remember the formula for a solution of a cubic, it's usually given for a cubic with no second term, right, with no quadratic term, because by shifting your variable x, you can get rid of this. So we will also assume that un minus 1 of x is identical equal to 0. So what this means is, you know, my variable x is not sort of God-given. I can change it. And I can choose a different variable t, and I can always reparameterize to make sure this happens. Okay? And scaling is okay. So let's consider such differential operator. And let's consider L2 equal to sum for I goes from 0 to m of some, say, vi. And the moment you cannot distinguish my u's and v's, please let me know, because this will be important. So, I mean, it's the same kind of thing with the same assumptions. So this means I'll assume Vm of x is constant, and I'll assume that Vm minus 1 of x is identical to 0. Okay? So this is not, I mean, I'm not losing generality. This is done without loss of generality so far. So, and yes, so now the main point is, yes, and assume that they commute. L1, L2 is 0. So this is to say they commutate as a differential operator. So this is a differential operator in X of order n plus m minus 1 in general. Otherwise, you cannot simultaneously do it. So if you have two commuting differential operators, you can renormalize both of them at the same time. I'm not going to prove it. So for us, let's just say this is a setup. So the setup, we have two differential operators with a constant highest term, 0 next term, whatever happens afterwards, they commute. And their commutator, it's a differential operator of order, whatever, 1 less. I mean, maybe in this setup, it's actually of order 2 less. Okay. Okay. So anyway, I mean, it's a differential operator that we assume is 0. So the question is, classify this. Classify such L1, L2. So during this hour, I'll tell you roughly what the answer is. There'll be one piece that I probably won't get a chance to prove because I'll want to say something else, and we'll return back to that next time. So how do I do that? So I'm going to go slowly because, I mean, I presume there are no experts in integrable systems here. So has anybody ever seen a solution to this problem? Read it? Knows it? Good. So we'll go slowly because I think it's important. So this is somehow the crux of the matter, that this is how people came up with the idea of studying, with the need to study the KP system, the KP hierarchy, by looking at this. So what happens is the following. So when do two, so let's consider the space of functions with certain properties. So it's a certain linear space. These are linear operators on this space. When do two linear operators commute? Well, if you can diagonalize them both simultaneously. So if there is a basis consisting of their common eigenfunctions, right? So sort of finding out whether two things commute is equivalent to finding out whether we can find sufficiently many common eigenfunctions. Okay? So this means we should be looking at eigenfunctions to start with, for one of them and for the other one of them. Okay? So this is an ad hoc method. I mean, I'm not saying that it's completely motivated at this point. So look at a formal variable. So introduce a formal variable. Formal variable k. And a formal power series. Psi, which will depend on x, which is this x, and k. So when I write a formal power series, usually you'll start with 1, and then it'll be k and k squared and so on. It's traditional in this method to go in the negative direction. So you start with minus 1. So I'll write here, this is going to be the sum of coefficients. I'll denote them psi s, for s goes from 0 to infinity. So psi s of x, k to the minus s. So I'll go in the negative direction. This is just a convention for which I think I should apologize to differential geometers and algebraic geometers, because you never do that. But that's somehow simple. And to give myself a little bit more freedom, let me even put an exponential factor here. So now this is a mess, because this is positive powers, right? I'm not claiming any kind of convergence or meaning for this kind of gadget at the moment, but this is just a series. So when I write this, this means I prescribe what kind of positive terms it can have. and this is an arbitrary negative term, then multiply by an exponential. Okay?
Yeah, PC is just analytic power series.
Yeah, this is. I have never really specified in which class we're looking. So let's say this is smooth functions on R or holomorphic functions on C. So this will be in the same class. So I mean, they will sort of be in the same class. So let's say these things were holomorphic functions on C to start with. The problem people really were interested in, I think, were smooth functions on R. But then they discovered the problem was actually algebraic. Okay? So they will be in the same class. So, and the question you ask here, can such psi for a fixed k be an eigenfunction of, say, L1 and maybe L2? So let's study L1 first. So, of course, for different cases, you'll get different functions, presumably. I mean, it should be. It's a power series, not trivial. So you can try to solve a bit more precisely L1 psi of xk. So what do I mean by this? I mean, this is a formal series of some sort. The coefficients depend on x. So I just differentiate the coefficients with respect to x. I leave the k alone. Nothing happens. So term by term, I know what this power series is. And I would like to solve. This is equal to kn psi xk. And maybe, to be generous, there is this highest coefficient here. So let's say times un. Okay. I mean, it's just a matter of how I choose my basis, essentially, that this un is there. Okay. So we can try to solve that. And you see I'm writing k to the n here. Why do I do that? Well, I want to have a family of eigenfunctions. And somehow k will be the parameter. And I want the eigenvalues to be different. So one way you could do that is you just put k to the n here. Why it's natural to put k to the n and not k here, it's a good question, but this is somehow the way the things will work out better. Okay? So this is what we try to solve. And of course, this is a completely ad hoc thing so far, and there is no reason that I have given you yet to believe that such a solution exists. Because I'm looking for this as an identity of formal power series in K. So this is much more than just requiring, y eigenfunction or two eigenfunctions. This is an identity for this function. So now it's an identity in K and X both, right? But you can ask whether this is true. So the first proposition is the following: that for any x naught, so x naught is a particular value of x, I won't specify where it lies, there exists a unique solution psi, which will denote psi x naught xk, such that this holds. And moreover, of course, I can take any such psi and I can rescale it. There is actually a lot of freedom in doing that. So to normalize, I'll require the following. I'll say that psi naught. Wait, I didn't mix up anything yet. Of x is identically equal to 1. I'll just fix this to be 1. And the way x naught will enter, that psi s of x naught will be 0 for any s greater than or equal to 1. Okay? So I'm just trying to say that the expansion that I'll get at x naught will be just 1. Right? So you could think that if I take such a solution, whatever it were, I could multiply it by an arbitrary power series in K, independent of x. This will not change this, of course, right? I'm just multiplying by a power series of K. L1 does not act on it. So I'm trying to get rid of this by just prescribing the value of at x naught. Okay? So this is a proposition I'd like to prove, which will justify, in retrospect, this choice, because it will mean that such a solution exists and is unique for any such differential operator L1, given a normalization that you choose at x naught. Questions? Okay. So now comes sort of the embarrassing part of the story. How do you think you would prove something like that? You would think there is some smart geometric argument or whatnot, right? But that's not how you prove it. You prove it by just expanding in power series and computing term by term. And I realize it's not so much fun, but I would suggest that we try to do it together, because this is a kind of computation that turns out to be crucial for what we do. So the point is, we're going to find inductively, starting from the assumption that psi naught of x is identical or equal to 1. Okay. So let's do this. I mean, maybe I'll only show some pieces of the computation, not the entire thing. And the problem, by the way, if you read the papers on the subject, it's customary to drop the entire computation if you write a paper. So if you read a paper, you will see this statement, you will see this as a proof, and there will be nothing else written, mostly. And this means you'll have to supply the computation, and the computation could easily be a page or two long. Okay? But this is how it works. So how do we do that? So let's take this L1, let's take this psi, and let's formally apply it and see what happens. Okay? So let me just write down the formula. So let's take just one term, and then we'll take the sum. So what will I get if I take, well, let's forget the ui for a second. So let's take di dxi of psi xk. So what do I get? Well, I'm taking the derivative with respect to x, right? So the x is here and it's here. So there are going to be two pieces. So the first piece is if I differentiate, well, let's take d dx, sorry. Let's do the simplest case first. So if I take d dx, so I differentiate either here, right? And then I get the derivative with respect to x. Sorry, I'll start writing like that, otherwise it gets really out of hand. Psi s of x, k minus s, e to the k x minus x naught, plus, and the other possibility is I differentiate over there. So the sum doesn't go anywhere. Oops, sorry. But now I differentiate here with respect to x. So if I differentiate here with respect to x, I get a k coming down, right? That's all I get. So k e to the k x minus x naught. Okay. So what does this mean? So here, of course, in the second term, I mean, this piece is equal to the sum for s now goes from somewhere else. So the lowest order term I was guessing, so now I'm shifting by s. So now it starts from -1, right? Psi s plus 1 of x, k to the minus s, e to the k x minus x naught. So now let's try to see what happens. So suppose we differentiate some more times, right? So if we differentiate more times, so I dxi of psi xk, what we're going to get is we're going to get, there'll be something like the derivative I times, so there'll be a sum for s goes from 0 to infinity, minus n to infinity now. And so I'm trying to avoid doing the actual computation, which may or may not be a good idea right now, of some coefficient that we'll discuss in a second, times k minus s times e to the k x minus x naught. Right? Because you differentiate at most n time, at most I times. Sorry, this was I. Right? So you differentiate at most I times. So whenever you differentiate here, you just differentiate. The power of k does not change. When you differentiate here, you get a k pulled up, down, and if you trace carefully, it starts from minus I. So in particular, if you were to take now L1 applied to psi xk, this will be a sum of certain coefficients from minus n to infinity of some coefficient corresponding to L1 k minus s times the exponent of k x minus x naught. Okay. So now what I would like to do is I would just like to start solving. So let's look at the lowest order term. So I want this to be equal to k to the n psi of xk, right? Which is the same as the sum for s goes from minus n to infinity of psi s plus n x k minus s times the exponent that's always there. Right? So the exponent I'll of course just cancel, and so now I want to equate the two sides. Oh, sorry, and there was un that I'm forgetting. Again, there is no high technology here. You're just solving an equation term by term in power series. It's a formal power series. I don't have to check any convergence or anything. I just need to check that inductively I can solve. The reason I'm doing this is in the proof of the trisecant, such techniques appear over and over again. And in some cases, you have to do a very lengthy computation. And when I'm trying to discuss these places tomorrow, I'm going to say, and now you solve term by term. And then in the good habit of the theory, I'll skip 2 pages of computations that you actually need. And sometimes I'll say, and in the middle of these 2 pages, some miraculous constellations happens, and you get the desired result. But this is how it works. So let's try to check what happens. So let's look at the coefficient of k, say, to the minus n. K, sorry, to the n. Right? So if s is minus n here. So how could we possibly get a shift by n here? Well, we have to differentiate the exponent n times. Right? So it means we'll get, so L1, we need to differentiate the exponent n times. Right? Because every time we differentiate an exponent, we pull out a k. And this coefficient can only appear here on the left-hand side. So left-hand side. So all we have, we're going to have just chi naught of x. Okay. Sorry, I mean I'm equating this side and this side after canceling the exponent because it's the same on both sides. And I'm trying to solve term by term. And in doing this, I'm also trying to write down explicit formulas for these coefficients and so on. Okay? So that's the left-hand side. On the right-hand side, you just have chi naught. And sorry, there is a un, I guess, then, because you're differentiating. And there is a un. So this is automatically true. So the way I arranged this was exactly to make sure this happens, because otherwise I wouldn't have any chance. Okay. And this exponent was placed here especially so that you can pull out the k's and solve term by term, and this is how it works, and so on and so forth. Okay, let's do the next coefficient. So the coefficient of k n minus 1. How can we get that? On the left-hand side, well, what do? We need to differentiate to get, so either differentiate the exponent n times, in which case if we're differentiating the exponent n times, it means we're getting un times psi1 of x. Right? Or we differentiate the exponent n minus 1 times, in which case we're going to get un minus 1 of x, and we're going to get the derivative with respect to x of chi naught of x. Okay. On the right hand side, well, we just get chi 1. Yeah, so we're trying to compute the coefficient of k to the power n minus 1. So it corresponds to the term where s is equal to 1 minus n. So on the right, there is just chi 1 and nothing else. On the left-hand side, we're supposed to get k to the power n minus 1. And we start with a power series that starts with 1. So we have to produce n minus 1 copies of k. So there are two possibilities. Either we produce n copies and then kill one of them. This is what happens here. Or we produce n minus 1 copies and don't kill any of them. Okay? So now notice we are lucky. We somehow assume this was identically 0. So this still works automatically. Okay? Well, let's go on. Coefficient of k to the n minus 2. And I'm sorry I'm doing this, but I don't want to write the general formula without any explanation. It's somehow, I think, very important that you see how this actually happens. So on the right-hand side, we certainly know what we're getting. We get un chi 2 of x. Right? What do we get on the left-hand side? Well, on the left-hand side, we can certainly differentiate n times, and then differentiate the exponent n times, and then get a k to the power minus 2. On the other hand, you can differentiate the exponent n minus 1 time and get, am I doing this correct? So let's check. So here I want to get the term that has k to the power n minus 2. Okay. So by differentiating this n times, I'm supposed to get k to the power n minus 2. So I have to differentiate this at least n minus 2 times. Each time I do that, I get a power of k. And then the question is how many times I can differentiate here. So every time I differentiate here, I don't get a k. So this is un minus 1 of x times the derivative with respect to x of psi 1 of x plus un minus 2 of x d squared x okay, 2 of x. Is that correct, or am I doing something wrong? Oh, yeah, there is multiplicity. Sorry, there is some binomial coefficient here. Maybe there is an n choose 1 here, and n choose 2 here. Hmm? Cosine. Oh yeah, yes. Sorry, you're right. There is something I don't like here. Hold on. So when I equate these two, this will disappear. I'll say this is 0, then I'll be in trouble. So I'm not computing correctly. So let's do this carefully. You can see there is a problem with doing computations on the blackboard. You make mistakes. So let's see. So let me take a step back and do something correct. So let's compute dx to the k of psi xk. And let me write down the coefficients correctly for once, right? So this is dkx of the sum of psi s of x k to the minus s e to the k x minus x naught. So this is going to be the sum goes from s is equal to 0 to infinity. So this is going to be the sum, and the sum is going to go over which of the two I'm going to differentiate. So the sum is going to go from I is equal k was a horrible notation, j. I goes from 0 to j, and this will be the number of times I differentiate each of the two. So there'll be a j choose I coefficient here, and then there'll be dx to the I of this sum times dxj of this thing. Okay? This seems correct. Now let's differentiate. So if I differentiate here, there is no choice. I have to get, so this is a sum for I goes from 0 to j of j choose I of the sum of s goes from 0 to infinity of the derivative, the i's derivative, this was j minus I, of psi s of x, k of minus s, times k to the power j minus I, e to the k x minus x naught. Okay. So now let me bring the similar terms together. So this is going to be the sum for s goes from minus j to infinity of k to the minus s times the sum for I goes from 0 to j, and this sum might be smaller, j choose I, dx to the power I chi s plus I. Okay, something like that. So this formula is correct, if you look at it. So what happens here is, of course, the derivative of chi naught of x is 0, because chi naught is, we define it to be 1, right? So I guess declaring that un minus 1 of x was 0 identically was not such a great idea, because in that case, I mean, we'll have some problem here. No, I mean, this is, sorry. This is still 0. And this is 0. So that's okay. So we're still safe, but we're still not getting anything useful. So now, sorry. So all of this was my mixing up in the interests of science, hopefully. And so if you look at now at coefficient of k to the n minus 3, eventually you should start getting something interesting. So on the right-hand side, you're going to get un chi 3 of x, and on the left-hand side you should get un chi 3 of x plus n choose 1, un minus 1 of x, the derivative of chi 2 of x, plus n choose 2, un minus 2 of x, the second derivative of chi 1 of x, plus n choose 3, un minus 3 of x, times the third derivative of chi 0 of x. Okay? So what happens now? So this is equal, this piece is equal to this. This is identically 0. Okay? This is identically 0. And I seem to have a problem, right? Hmm?
So are you constructing this side?
I'm constructing, so my goal, so
You just solve that the ordinary differential equation. You can find.
But do I really have an ordinary differential equation? I have something equal to 0. So I wanted to have something, so I wanted to argue that eventually I would be getting the derivatives which would be non-zero, and that so what I thought was going to happen was that I was going to compute these things recursively. So I was going to say that this is my derivative. So I was going to say that L1 psi xk I can now express in this form. So the coefficient of k to the minus s is going to be u, some sum over I goes from 0 to j of some u's times some derivatives of psi of appropriate kind. And then I was going to try to solve this inductively step by step. But something seems to have gone wrong for me in the sense that I seem to be getting zeros all the time. So the inductive solution seems to be giving me zeros. And we need to find a mistake, or you need to trust me and we need to move on. But of course, giving you a wrong proof is not a good idea, so I should rather find a mistake. Okay. So again, on the right hand side here, the coefficient of k to the minus s is certainly chi s plus n times un. Right? That's the coefficient of k to the minus s. On the other side, so you get the sum. So let me write this correctly. So let me copy from the original paper. Then maybe it's better than if I copy from this formula. So the sum for I goes from 0 to n of the sum, this was a j, right? I goes from 0 to j. So for this one, you're supposed to have the coefficient uj of x, right? And this, and then you use this formula. So then you get the sum of ji dix chi s. This should be plus. Okay, which is what we're getting. I mean, it's a plus because we're counting in the opposite direction. Okay, so this is what we're supposed to be getting. So this means that for the k to the minus s coefficient, we're supposed to have this sum. So the sum for j goes from 0 to n of uj of x. The sum for I goes from 0 to j of j choose I. The i's derivative chi s plus I. of x, yeah, I see what the mistake was. I missed some terms. Is equal to what we're getting there, which was chi s plus n of x, un of x. Okay. So let me go back here. Let me apologize and let me try to use this to get the correct formulas. Okay. So let's just see. So for the coefficient of k to the n minus 1, right? So this is k to the minus 1 minus n. So this means we need the shift here, this shift by which we are shifting, I to be at least n minus 1, right? So we have un of x times no shift plus dx chi 1 of x plus un minus 1 of x chi 1 of x is to be equal to un times psi naught of x. The formula we had before, I was missing one of the terms. More precisely, I was missing this one. Okay. So now I would like to claim that I can recursively solve. So we can solve for dx by 1 of x. Okay. Because this is 0, so I can solve for the remaining thing. And use then the value of chi 1 of x naught to get chi 1 of x, and not only the derivative of chi 1 of x. Okay. And then as the next step, the coefficient of k to the minus s would involve the size s plus epsilon, which we chi s and up to chi s plus n, right? And the derivatives. So inductively, if we know chi s plus n minus 1, we'll be able to solve for chi s plus n. We'll actually be able to solve for its derivative, because that's what will appear, and then using the fact that we know that any chi s plus n at x naught is 0, we'll get chi s plus n. Again, the idea is simple. The computation was not correct as stated, but the idea is you just solve term by term. Okay, sorry. Okay, so why did we do all of that? Because now we have this unique construction of a solution. So the next proposition you would like to prove is the following. Any solution of L1 psi of xk is equal to kn psi of xk times un has the form psi x naught of xk times a of k x naught, where this is independent of x. So the solution I chose in the beginning was just a solution that was normalized to kill the power series. So now I'm saying I can, of course, multiply by any power series. This power series will depend on x naught because I kill the power series at x naught. Okay? So this hopefully is essentially self-evident that you can take the solution and the freedom you have is multiplying by any power series. So I'm claiming, so proof, so this is certainly a solution because L1 doesn't really act on this. Right? L1 doesn't differentiate at all.
Is it the A is the polynomial of K or just
It's a formal power series in K. So it can be any formal power series of K with coefficients depending on x naught. Okay. So now I need to show, so we need to show that any solution has this form. So let some psi of xk be a solution of this. I then want to check that it will have this form no matter what x naught I chose. So how am I going to do that? So we're just going to construct it by hand. So we let a of k x naught be by definition equal to psi inverse, let's see which one, of x naught k times psi x naught of x naught k. This is it. You just construct, you just show what this a of k x0 is, and then of course you see that psi of xk times this a k of x naught is still a solution of the original equation, but now it is normalized at x naught and thus is equal to psi x naught. So all this says that is that the only freedom you have in choosing a solution is by multiplying by an arbitrary power series in K. To get from one x naught to another, that's all you can do.
I have some question with the notation. What is bracket of L1A?
This is the commutator of this as operators of an x. So I'm trying to say that L1, it's a differential operator in x. There is no x here.
Yeah.
X naught is just a fixed parameter. So I'm trying to say that L1 does not really differentiate anything here. So if I try to apply L1 to the product here, it's the same as if I multiply by A first and then I apply L1 here. And since L1 applied here gives me k to the n times z, then L1 applied to this whole thing will be k to the n times z times this. I'm saying the following. L1 applied to psi x naught of xk times a of kx naught is going to be the same as a of kx naught times L1 of psi x naught of xk, which is the same as a of kx naught times k to the n psi x naught of xk times un, because this is an eigenfunction, and this is of course the same as k to the n un times a kx naught psi x naught of xk. So this means this object is a solution of, is an eigenfunction as we wanted it to be. So all this says that was that this is a differential operator in x. So if you multiply by anything that's constant in x, it doesn't change the eigenvalue, the fact that this was an eigenfunction.
What is the inverse of sine?
That's a formal inverse of a power series in k. I don't know. And the exponents, so there are exponents floating around, you just combine them together. But the power series you formally invert. Okay. Okay. Now the point of this construction was the following theorem. So remember we started with L1 and L2. And the statement was that L1 and L2 commute if and only if the following holds. So you can take psi inverse x naught of x naught k, right? And then you take L2 and apply it to psi inverse. Evaluate at x equal to x naught. Okay. So this is independent of x naught. So let me explain what happens here. So you have this for any x naught, you have a construction of a solution called psi x naught, which is normalized at x naught. And then this is a solution. This is an eigenfunction for L1. Now I want to know whether L1 and L2 commute. And they say they commute if and only if essentially psi x naught is also an eigenfunction for L2, but in this precise way. So this is a formal power series in K, which I cannot get rid of, because if I wanted to ask whether this is a solution for L2, it may not be normalized properly, so it will be a power series. But this power series will no longer be able to depend on K. So let me give a proof. So the point of this is somehow to say that L1 and L2, if I want to solve this, it amounts to knowing some properties of psi. So if L1, L2 is indeed 0, then of course L2 times psi, any psi, anything like that, is an eigenfunction of L1, right? Because you can permute them in the opposite direction. So xk. So this means then, by the previous statement, that L2 psi x naught of xk must then be of this form. It must be equal to psi x naught xk times a certain a of k x naught. Okay. On the other hand, for any x1, so the point is here we want to move from point x naught to point x1. So if I choose, take psi x naught of xk and multiply it by this, is also an eigenfunction of L1. Because this does not depend on x, so certainly it didn't change anything. So this is equal to psi x naught xk times a certain power series b depending on k and x naught. Okay. So now let's try to compute a of k x1 for some for x1 but instead of x0. So this has to be equal to b inverse of k of x0, a of k of x0, b of k of x0. Just because on the other hand here, I mean, I can also take psi x1, right, and psi x1 times e to the k x0 minus x minus 1, and I can take this. And I'll get, I mean, this is true for any x0. So I can plug in x1 instead of x0 here. Okay, so this means a of k x1 I can then convert from here, because this is also a solution and it's also normalized the appropriate way, so I get this. But then this cancels. So a of k of x1 is equal to a of k of x0. The purpose was that I knew explicitly how to sort of pass from normalization at x0 to normalization at x1. I use this here, and then I know that on the other hand here this has to be a dependence, and this all commutes, so it works. So this is in fact the part that's not as exciting. Somehow it's much harder to show that two things commute in general than to try to derive some consequences of their commutation. So on the other hand, so suppose on the other hand that we know that L2 psi x naught of x k naught is equal to psi x naught of xk times a of k, which is what this thing says. Yeah. So then let's try to compute the value of the commutate of L1 and L2 on psi x naught. I claim this is going to be 0, because you see, I mean, this is the same as L1 L2 psi x naught minus L2 L1 psi x naught. Right? And here, all L2 does, it creates an extra power series on K, which doesn't interfere with A at all. Okay. So we get this. So thus, I want to say that L1, L2 is 0. Why would that be the case? You see, L1, L2 is a differential operator in X of finite order. Thus, its kernel is finite dimensional. And it cannot contain psi x naught for all x naught, unless the differential operator is 0. So far this has not had anything to do with curves. The main theorem in this study is the following theorem. This is due to Grushevsky in 77. And that's the following theorem, that if we have L1 and L2, two commuting differential operators as above, then L1, so you see the condition that you have such a pair actually imposes certain restrictions on L1. Because you can see that this, this eventually you'll be able to reinterpret as conditions on L1 itself. Then L1 has an eigenfunction psi of xp for p lying on a certain curve. So curve in mg. The genus could be arbitrary so far as we are concerned, as far as we're concerned, where the eigenvalue is going to be as follows. Such that the following are true. E of p is a meromorphic function on the curve C with a unique pole of order n at some point p naught. Okay. So this means we have a family of eigenfunctions such that all of the eigenvalues are sort of bounded except for one of these eigenfunctions, sort of psi at x p naught, is not such a good eigenfunction. L1 is still a differential operator and x, p is just a parameter. And the function psi itself, psi of x p, as a function of p, has is meromorphic on C without p naught, has g zeros, p1, pg, independent of x. And finally, if you let k of p to be u of p over un to the power of 1 over n, so it's a function on the Riemann surface now, constructed from u of p and this coefficient un that we had for L1, then, so notice I said meromorphic on outside of p naught. Then the condition is, let me write it here. That if you take psi of xp and you multiply it by the exponent of minus k of p x minus x naught is analytic near p naught with value 1 at p naught. Okay. So what actually happens here? So you see the function e of p has a pole at p naught. That's what this says. But it's not just a pole, it's an essential singularity. Sorry, e of p has a pole of order n. So when I take k to be e of p divided by something, never mind, to power 1 over n, this is sort of a local coordinate near the point p such that k inverse, so k of p naught is infinity, right? Because, and it's a simple pole, because e of p had a pole of order n, so its nth roots had a regular pole. So this means k of p has a simple pole near this place. So what this tells you is that the function psi of xp near p has an essential singularity of the exponential type. So this is to say that psi of xp has an essential singularity of the kind e of to the k to the px near p naught, essentially. And this thing is here to kill this essential singularity and make the whole thing regular.
What is G?
Hmm?
What is G?
There given L1 and L2, there exists such a curve, and there exists such a collection of points. The curve has some genus, which will somehow depend on L1 and L2. And we can discuss where the curve comes from, and we will. But I didn't say this yet. Okay. So this is how you see such a how the curve appears in the theory, and the curve actually appears as a spectral curve. Which is to say that, in fact, if L1 and L2 is 0, then there exists a polynomial q in two variables such that q of L1, L2 is 0. Okay. And what happens is that the space of L2 commuting with a fixed L1 corresponds to the curve Q of L1, L2 is 0 as a curve in P2. So there is sort of a nice one-dimensional family here. Okay, and this is the curve. So it naturally occurs as a plane curve, not just as an abstract curve. Then you can worry about its singularities and resolving the singularities, and in general it might have singularities. But that's another story. Okay, so since I'm already greatly over time, I should probably stop. So next time we'll start by going in the opposite direction. We'll get a curve, and we'll see how a construction of such a function psi will give rise to operators L1 and L2 that commute. So this will then show that the set of data, a pair of commuting differential operators, and the curve with the data of such a function are equivalent. Okay, this will be the beginning, and then we'll do the proof of the trisecant conjecture, and hopefully I won't mess up the next power series computation. Thank you for listening.